We are going to discuss the idea of goodness of fit and statistical significance of parameter estimates. Whenever we estimate a parameter, we have to somehow, based on the data, make a decision: is there a parameter to be estimated in that particular problem, or how many parameters should be estimated? So the way we formulate this is in the form of a hypothesis testing. If we have a set of parameters we are estimating for fitting a polynomial to a number of data points, it's not clear what is the appropriate order of the polynomial. There is a small result which I like to quote that is relevant to this question, stating that through any 3 points on a sheet of paper, one can pass a straight line. For those of you interested in the mathematical proof, here it is. Use a pencil that is thick enough. So, coming back to our problem, we are given a set of data points. In this case will be scalar measurements. And when fitting a polynomial to these points, we can encounter 2 situations. If the order of the polynomial we chose is too low, namely we are underfitting it, clearly the fit will be poor. At the other extreme, if the order of the polynomial is too high, in this case we are overfitting, it turns out that the estimates of some of the parameters are not statistically significant. Namely, they are buried in noise. They are pure noise. No such parameter is there. So we have to make a decision based on imperfect data how many parameters we should use in a particular problem. That's like a model selection problem. Now, there is one result which is proven in 362, and this is the following. The sum of the squares of the residuals in a least squares estimation problem, namely the minimized value of the least squares criterion, I was given in 3412, which we also call the goodness of fit or fitting error. This is J star, for star in this case standing for the optimized or the minimized value of the function J. This expression, which is a quadratic form, with x inside, was the criterion according to which we carried out the minimization, or on which we carry out the minimization, and therefore according to which we come up with the estimate. And now, if we find the estimate x hat k and put it back into the criterion, we can look at the resulting number, which is a scalar, as a measure of how well the model we used fits the problem. Statistically, if those noises are Gaussian, because what to measure is z is hx plus w, so the w noises, if they are Gaussian, it turns out that this quadratic form would have a chi-square distribution with the number of degrees of freedom equal to k, that's the number of measurements, and z is the dimension of each measurement, so that's k and z, minus nx, which is the dimension of x, that's the number of parameters we estimated from the problem. Now, the way we do the test for underfitting is as follows. The order of the polynomial fit to a set of data points is too low if the fit is not good enough. Namely, the minimized value of j, that is j star, is larger than some constant, which is a tail point on the probability distribution of the chi-square density, with k and z minus nx degrees of freedom, and this is an alpha probability at the tail, and this is the 1 minus alpha percentile or point on this distribution. Typically we use alpha as 5%, and therefore what we say is, if the goodness of fit cannot be explained by the unavoidable noises, namely it is way out in the tail. By way out, again, we mean past the same 95%, possibly 98 or 99%, these numbers are somewhat subjective, then our model really gives a poor fit. You will always have a fitting error because of the noise. The question is, if the noise does not provide a reasonable explanation for the fitting error, then there's something wrong with the model. In this case, if we start with a polynomial that has an order that is too low, you can increase it until an acceptable fit is obtained, namely the resulting J star falls below the maximum allowed. And we'll illustrate this in an example. Before that, we'll look into the test for overfitting. Now, if the order of polynomial is too high, which means we have terms in the polynomial, coefficients we are trying to estimate, which are not in the truth, in the real thing. But we don't know the real thing, so we'd like to infer from the estimated values whether to accept that there is such a parameter or its value is 0, means there is no such parameter. And that's what we say. In the case where we overfit, say typically what would happen is the highest power coefficient would be statistically insignificant. Namely, we can accept the hypothesis that it is 0. Assuming the noise is to be normal with 0 mean and known variances, the estimate of the ith component of the parameter vector, that's x number I hat, would be Gaussian, with mean xi and some covariance pii. Now, the significance test of such a parameter estimate x hat would be the test between the two hypotheses. First is simple, second is really not simple. H0 that xi is 0 and h1 that xi is non-zero. So the first case means there is no parameter number I. Second, yes, there is a non-zero value for it. And this will be done subject to probability of accepting h1, namely accepting that there is such a parameter when there is no such parameter, namely h0 is true, being a small number alpha. In other words, we are willing to make an error of, say, 1% to 5% or so, that we falsely accept the existence of such a parameter. In this case, we would accept h1, namely that the parameter is non-zero, if and only if the magnitude of the value of this estimated parameter in magnitude divided by the standard deviation associated with this estimate is above some constant c prime, which would be obtained again from the tails of the Gaussian density. Now we cut alpha over 2 on each side. So a total probability, because we don't know whether it's positive or negative, total tail probability will be alpha. So this is a two-sided probability region, and the threshold C prime can be obtained from the tables we have seen in subsection 154, such that the probability for a standard Gaussian random variable exceeding it is alpha over 2. For 5%, what you have is 1.96, namely that's 2.5% on each side. So the plus minus 2 sigma rule is effectively used in this illustration of the significance test for a parameter. Now, if this ratio, the significance ratio we are using here, does not exceed C prime, then the estimate of the parameter is said to be statistically insignificant. We discard it and we accept the null hypothesis, there is no such parameter, and solve the problem again for a lower dimension parameter obtained by deleting the component found insignificant. Let's take a look at a nice example, a polynomial fitting example where the true parameter vector is of dimension 3. It is a second-order polynomial. It is a constant acceleration motion that models the truth. But we don't know, and we would like to reach the same conclusion that indicates the order being 3, namely a 3-parameter, the order of the fit, the dimension of the vector is 3, really it's a second-order model. The second-order model obviously has 3 coefficients in the polynomial, because that's what a second-order polynomial has. So the measurements now are given by z equals to the polynomial model with an x1, x2, and x3, our parameters. You can see this is position, velocity, acceleration, second-order polynomial, plus noise. Wi would be the independent noises, and we assume for the sake of illustration values x1 10, x2 1, x3 0.2. We have 15 time samples. They are centered at 0, so this expression gives us the values of the times at which the samples are taken. And the noise sequence is white, zero mean, and unity variance. So what these are the measurement noises, the disturbances in our observation. Now, here is a table that shows the results of fitting a sequence of measurements generated, and this is a single sequence now. From one sequence of measurements, we should be able to reach a conclusion. And we have the option of using a first-order polynomial, that's 2 coefficients, second order, 3 coefficients, third order, 4 coefficients. So the assumed order nx is 2, 3, 4. That's a linear, quadratic, cubic motion model. And if we look at the results of the estimation from one single run, one single generation of those 15 measurements, assuming a linear model, a straight line fit, we get the estimate of x1 as 11, 12 almost, its standard deviation 0.2, and we look at the ratio between the estimated value in magnitude and its standard deviation is 46, way above 2. Clearly it is significant. Then we look at the second one, x2 hat. We end up with a value around 1, its standard deviation around 0.06. The significance ratio is almost 17. So what we have now is 2 parameters, both are significant. So there is no problem of overfitting. Is there a problem of underfitting? Let's look at the goodness of fit, the J star, which turns out in this case to be 44 and something, and then look at what we expect it to be the highest value with 95% probability, so excluding a 5% upper tail. We have 15 measurements, so it will be 15 minus 2, 13 degrees of freedom. It should not exceed 22.4, but it is about double of it. Therefore, it is an unacceptably poor goodness of fit. Therefore, we use the model which does not have enough parameters. Next one, we go to quadratic. Now we have 3 parameters. Again, for the first parameter, 10 divided by 0.4 or so is 26 something. Yes, significant. Second parameter, around 1 divided by 0.06, significant, 16. Third parameter, estimated value 0.174, standard deviation 0.03, ratio, significance ratio 5.6. All of these are significant. Do we have an acceptable goodness of fit? Again, the goodness of fit will never be perfect because there are noises. So within the natural variability of the noises, we take a value we look for a value that is acceptable. Now J star from our run turns out to be 13 and something. The value that is the limit of acceptability is 21, and this is based on the 95 percentile, 5 percentile cutoff of the chi-square distribution with 15 minus 3, because now we have 3 parameters, so we have 12 degrees of freedom for the goodness of fit, and it should not exceed 21. It is well within that range, which means we have no problem. This looks like neither under nor over the size of the model. Now, for the sake of illustration, we go on and estimate a 4-dimensional model, which is a cubic third-order polynomial with 4 coefficients. Again, the x1 is significant, 26. x2, 7 point something, significant. x3, 5.6 something, significant. x4, the value estimated is 0.02. The standard deviation associated with this fourth parameter's estimate is 0.025. The significance ratio is 0.8. That's well below the 2. So we say that we got this value, it's pretty much buried in the noise, and there's no evidence in the data that there is need for a fourth coefficient, really the cubic fit. It's an overfitting, and therefore we can declare that this is an overfitting and discard x4 and go back and live happily ever after with a third-order model. Now, there's one more thing here that you can look at, and this goodness of fit for the fourth-order model, the overfitting, turns out to be a little bit better than for third-order. Obviously, with more degrees of freedom, more parameters, you will fit better. It is below the now 15 minus 4, 11 degrees of freedom chi-squares 95 percentile point, but that means, all it means is the fit is good, but the fit has an unnecessary fourth parameter. And therefore, because of this, this model is an overfitting. Now, let's go back and see another important thing, why it is not a good idea to overfit. If you look at the standard deviation in the quadratic and cubic, the okay fit, the good fit, and the overfitting for the x1's position, same standard deviation. Look at x2, that's a velocity at the center point of the batch of those 15 measurements. Look what happens. The quality of the velocity estimate, the standard deviation, has gone up by 2.5, a factor of 2.5. You pay the fact that we added the fourth parameter, we pay for it in a degradation of the quality of the estimate of x2. So x1 is the same, x2 is substantially worse, x3 turns out to be the same. In this case, they alternate as to which gets worse. Only one, every other parameter suffers from the overfitting. Next time it would be the x1. If I would go to quartic, that's 5 parameters, the x1 and the x3 would suffer. But in any case, it's important that what we did now is we spread out the available information among 4 parameters, and therefore we end up with one which is useless, it's meaningless, statistically insignificant, but we also significantly degraded one of the other parameters. So here's an additional reason why we should not overfit. Okay, to summarize, for the linear model, the J star was too large, well above the threshold, the 95 percentile point, therefore unacceptable. The quadratic model, that's nx equals 3, J star was below the threshold, therefore it is acceptable, and all the parameter estimates are significant. We see no problem with nx equals 3. The cubic model, nx equals 4, the last parameter, which is third derivative of the position jerk at the center of the batch, is statistically insignificant. 0.8, it should be not less than about 2. And furthermore, the fit has only slightly improved. It turns out there's a so-called F-test in statistics would indicate that the improvement in the fit is statistically insignificant. The fact that you get a statistically insignificant parameter goes hand in hand with the improvement in J star being insignificant. So these two are equivalent tests. Clearly, the nx equal 4 is a situation of over-parameterization, and the penalty we pay, as mentioned before, is that the velocity standard deviation is about 2.5 times larger if nx equals 3 versus nx, much larger than for nx equals 3, at nx equals 4 versus nx equals 3, because of the fourth parameter. Here are the figures that show the points which are generated around the parabola. Here is what happens if we have a straight line fit doesn't look good. These upper and lower solid lines, not quite straight lines, they are more like parabolas, are going to show the accuracy of the extrapolation from the center point of the batch. If you want to predict the position, you use the position, velocity, and acceleration, whatever you have at the center of the batch, and you predict it, and you end up with some kind of a accuracy of that prediction. Clearly, because this is an inadequate model, the actual points are way outside where they are predicted based on the center of the batch. That is equivalent, again, saying this is a very poor fit. The quadratic with nx equals 3 parameters, things are reasonably well. These are 1 sigma deviations, therefore it doesn't mean that if they are outside it's bad, because they can typically be at 2.5 sigma. Now, the third part of this figure is the over-parameterization, and you can see that the penalty you pay if you go and predict outside your variances, standard deviations are plotted here, will be much larger, and that goes hand in hand with the fact that the second parameter's standard deviation, the velocity estimate at the center of the batch, was degraded from here to here. And you can't see it in the middle because it's not yet visible, but as you try to extrapolate outside the data, at the edge of the data set, you already can see the difference. Okay, so these are called uncertainty tubes, 2 sigma confidence regions around the position, the predicted position. Next, what we are going to do is solve a real-world problem, bearings only target motion analysis. The problem is as follows. We defined the nonlinear least squares problem that can be used to estimate the motion of a parameter, of a motion parameters of a constant velocity target. And this is the so-called target motion analysis. But now what we are going to use will be observations from a passive sensor which measures only the direction of arrival of a signal emitted by the target. This signal can be noise, any target moving does emit noise, or it might be a tone, a narrowband emission from the target. So in most cases the emitted energy is acoustic, in other cases it is electromagnetic. You have a moving platform which emits some kind of a signal. So this is really called passive localization or passive arranging, because what you observe are angles, direction of arrival angles. You don't know the range. You want to infer the range based on a collection of such passive angle-only observations. In this problem, the target is moving in a plane and is observed from a platform with known position psi p and eta p at time k in the same plane. The target's localization vector is a vector of dimension nx4 in this case, because it will consist of two components, initial position and its velocity in Cartesian coordinates. So psi 0, eta 0, psi dot, and eta dot. And we assume that the target is moving with constant velocity. Clearly, this is a restrictive assumption, but it does hold in practice over a reasonably short period of time that in many cases is enough to localize, to find the range of the target from the passive observation. So we have a four-dimensional parameter vector. The position at time tk of the target, psi k or psi tk, these are two different notations that we'll use later also, sometimes just the index, sometimes the actual time indexed, is the initial position, psi 0 plus psi dot tk, or x1 plus x3 tk. So this is the x-coordinate, but we use the psi and eta terms not to confuse with these x's here. And the eta is x2 plus x4 tk, and this is the value of eta at time tk. So these are the two positions. So we have, number one, the basic parameterization of the problem. Number two, the actual location of that object based on the basic parameters, which is the vector x. The third step would be to express the measurements in terms of the position than in terms of the basic parameters of the problem. So we assume now that the available measurements are bearings, angles, line of sight angles with respect to some reference location, and that's all, nothing else, given by zk, which is another notation for z of tk, is h of k and x plus wk. Wk will be noise. Hk is the angle, that's arctangent, the difference between the eta of the object of interest and our eta, platform eta at time k, divided by the psi of the object of interest minus psi of the platform. So this is the angle observed without noise, but we measure it with noise. And we assume that the noises wk are zero-mean Gaussian white sequence with known variance r. Assume we know the instrument, the device with which we are measuring these angles. So the EWKWJ is a little r, that's the variance, times delta kj, and this is the Kronecker delta, equal to 1 if k and j are the same, equal to 0 otherwise. Now, before we try to solve a problem where we want to estimate a parameter, we have to make sure the parameter is estimable. We can estimate it. Do we have enough information in the data? Now let's look at the observability of the target parameter in this passive localization problem. It turns out there will be an effect of the motion of the platform. Up to now we said we know where the platform is, psi p, eta p at time k. But the question is, what should that be? Not only known, it turns out there will be some requirements on the platform motion in order to be able to estimate the motion parameters, the four-dimensional vector of the target. What we are going to show is that if the platform moves with constant velocity, the target motion parameter cannot be estimated, is unobservable. From a constant velocity platform with angle-only measurements, you will never be able to find out the distance to another constant velocity object. How do we see this mathematically? We'll denote the platform velocity components as psi p dot and eta p dot. Then the true bearing, ignoring the noise, is arctangent eta t minus eta pt at some arbitrary time t over psi t minus psi pt. Now what is eta t? Is eta 0 plus eta dot t. The eta p is eta p0 minus eta p dot t. So this is the target y coordinate, eta coordinate, the platform eta coordinate. In the denominator we have the target psi coordinate minus the target psi coordinate, all of them at time t. And again, we are expressing, here you can see there's an eta 0, eta dot, psi 0, psi dot. So we are immediately expressing the current position in terms of the basic parameters of the problem to see if all those four parameters can be estimated. And a little bit of a manipulation here, just group the positions here and the velocities here. And then what you observe is an angle. And look at the fact that this ratio with the original true values that we don't know for eta, eta dot, psi, psi dot, or a difference between eta 0 and eta p0 multiplied by alpha, eta dot, eta p dot multiplied by alpha. Same thing for the psi. For any alpha 0, we have exactly the same angle, which means if you double the distance between them and they move twice as fast, everybody moves twice as fast, you end up with exactly the same observations, which means you cannot figure out, there is some indeterminacy, and you cannot figure out effectively the distance and the velocity of that object in this case. So, what this shows is a situation in which we cannot solve the problem. So, you will obtain for all alpha the same sequence of two bearings if the relative position and the relative velocity are multiplied by an arbitrary constant alpha. That means if it's twice as far, relative motion twice as fast, you get exactly the same measurements. Thus, an infinite number of values of the target parameter vector can yield the same observations, and consequently this parameter vector cannot be estimated. The observability requirement is for full and unique recovery of the initial state, that's position and velocity for the target, is not satisfied. Therefore, in order to estimate the target parameter vector, the platform has to do something. It turns out that if the platform has an acceleration, it will be able to estimate a constant velocity object parameters in full. So constant speed platform with a change of course does satisfy this requirement. It is of practical consequence that you can use a constant speed that's easy to move at the same speed and just change the course, and therefore that will generate the observability, will allow to estimate the parameters. There is a general theoretical result which says that the platform trajectory has to have one more non-zero derivative than the target trajectory. The constant velocity trajectory has derivative, the highest derivative that's non-zero is the first. If the platform has acceleration, has one more non-zero derivative, the second, therefore the condition is satisfied. But practically you would not want to implement a constantly accelerating platform, but rather implement it with a constant speed and just change the direction of motion. Here are some examples. This is the platform. This is the target. If the platform doesn't move, has really no velocity, and the target is here, or the target is here, you can see the distance has gone up by a certain factor, and the velocity has gone up. What we get here is exactly the same sequence of observations. Here's another example. The platform is moving at constant velocity, the target is moving at constant velocity. But there is, at least, there's an infinity, but we are just showing another motion for the target which will yield exactly the same observations, because the observations are angles of this line of sight, second this line of sight, third this line of sight. So you can see that if the platform has no velocity, zero velocity, the target has velocity, actually the platform has one derivative less. The second case has the same order derivative, non-zero, first. Neither of these yield observability, complete observability, and the easiest way to see this in such a graphical manner. Here's another example. If the platform moves and the target is stationary, now the platform has first derivative, the target has only zero derivative, yes, this is observable, and this is just triangulation. Here's another example. The target moves constant velocity, the platform has an acceleration. Again, this will yield observability.